if we look at the inputs, nitrogen fixation and terrestrial nitrogen input, outputs mainly denitrification, water column and sedimentary denitrification. Both of these are large outputs or loss of nitrogen from the ocean. Sedimentation is a small factor. Okay, I've talked about this already, so I'll move on. So denitrification occurs where oxygen concentrations are low. And again, that's in sediments near the sediment-water interface, and it's common in shelf and slope sediments where there's high nitrate concentration, high organic matter supply, and low oxygen in sediments. And it also occurs in areas where there's high production and sluggish circulation, the Eastern Tropical Pacific and the Arabian Sea. There are feedbacks. And you can think about these feedbacks. If you increase the supply of organic matter, what happens? There's a lot, it rains down, you increase respiration, it sucks up oxygen, oxygen goes away, nitrate's present as an electron acceptor. So you have enhanced export, that's going to increase sedimentary denitrification. But that's really dispersed over a really big area. And so there's feedbacks, but the feedbacks are fairly weak, and they're spatially and temporarily separated. So where there are fast feedbacks or rapid feedbacks is in the water column, because the region of denitrification is very close to the region of production. So again, there's that feedback. If you increase production, it rains down, you increase denitrification. But if you increase denitrification, there's less nitrate that is delivered back to the surface, and that will slow denitrification down. But that feedback is strong. It's strong because it's both temporarily and spatially near one another. So we have good feedback. The regions that are important are the Eastern Tropical North and South Pacific and the Arabian Sea. Again, this is dissolved oxygen at 250 meters, so 250 meters below the surface. Oxygen is basically not measurable. There have been cruises where 60 meters below the surface, you collect a sample of water and you can't measure oxygen in it. It's so low. And that's from the Eastern Tropical North Pacific. So those are the regions that are important. We can look at the change in the nitrogen isotopic composition of sedimentary nitrogen with time in three regions: the Mexican margin, the Eastern Tropical Pacific, the Somali margin, the Arabian Sea, and a region in the South China Sea that's completely separated from surface water denitrification, or intermediate water denitrification. And what we see is that through time, there's high denitrification in the Eastern Tropical Pacific and moderate denitrification in the Arabian Sea, and it changes through time over the last 50,000 years. Okay, so in the it was fairly high in the warm interglacial, and then it kind of crashed in the glacial periods, so low in glacial periods. But over that interval where denitrification is changing a lot in these regions, the values that we find for an area separated where there's no denitrification near it in the South China Sea remains at this 5 per mil. So the residence time of nitrate in the ocean is what, about 3,000 years? So what we're seeing is a balance between denitrification and nitrogen fixation. Despite these big changes implied by the secular change in the nitrogen isotopic composition of nitrate, nitrogen in sediments as a function of time, it's balanced by nitrogen fixation. And the evidence for it is the constancy in regions separated from zones where there's a strong oxygen deficient, there's a strong oxygen deficient zone like the South China Sea that remain constant. So what we're looking at are these feedbacks, and the feedback is slow enough that nitrogen fixation can balance rates of high denitrification and nitrogen loss. So the resupply of nitrogen to the ocean through nitrogen fixation is balancing it through time. This is a way of looking at it. We have an N to P ratio here that's 16:1 from phytoplankton. That biomass is respired. It releases nutrients with an N to P ratio of 16:1. If that upwells through an oxygen deficient zone, there's denitrification in anomox, so that the ratio of these nutrients as they're upwelled is less than 16:1. Okay, if you have particles settling from this, it would have a high delta 15 N value. But nitrogen fixation is replenishing that N to P ratio, and it brings us back to that Redfield ratio. So over time, this cycle is dominating. Here's a nice figure out of one of Angel's papers that, here's denitrification. We enhance denitrification, we lower the N to P ratio. We upwell it here, and then the N to P ratio is low, you run out of nitrate. But that nitrate is resupplied through nitrogen fixation, which adds that N to P ratio back, enhances phytoplankton respiration, and it comes back down, and denitrification will be enhanced. So it's sort of this Gaia hypothesis where it's balancing. And the balance seems to be through this constancy or the maintenance of this N to P ratio on a basin-wide or ocean-wide scale through time. Okay. So the summary is nitrogen fixation is really crucial for maintaining this biological productivity. It replaces the nitrogen loss through denitrification on a number of different timescales. The factors controlling rates of nitrogen fixation, it's widely held that the rate of supply of iron to N2 fixing organisms is rate limiting, but also this differences in the N to P ratio can drive that nitrogen fixation. And it stabilizes this oceanic reservoir of fixed nitrogen through time. Okay.